All right, hello and welcome everyone to our next video in the complex numbers theories. We are on part number 8 and we are going to be talking about the Moivre's theorem and complex roots. So make sure you are following my socials. Ask me which course you would like to see next and put that in the comments, please. And let's dive right in. First part, the Moivre's theorem. What is this theorem? Remember, a theorem is just like a rule or a way of doing something. And here, this is what the Moivre's theorem is telling us. Z to the power of n is equal to r to the power of n cis n theta. Well, if we think about this a little bit more, we can actually get to this quite easily. Because remember, z to the power of n is z times z times z n times. And how do we multiply numbers, complex numbers, in polar form? Well, moduli are multiplied. So the modulus of z times the modulus of z times the modulus of z n times. Well, that's r times r times r to the n, which is exactly what we've got here. And what do we do with the angles? The angles are added. So whatever angle we have for z, we're going to add it, n amount of times, and we get this formula. So that is not really a formula that we couldn't already think of ourselves, but later on we're going to see n doesn't necessarily have to be a whole number. It can also be a fraction. So let's just apply this rule with an example. We have z is 5 cis pi over 8. So if we want z to the power of 8, well, we need r to the power of 8, so 5 to the power of 8. And we need to multiply the angle by 8. Well, that was pretty easy. Chuck that in the calculator. We get 5 to the 8 cis pi. What about z to the 10? This was a question in our last video that we were looking at that we thought was really tedious. Well, let's do it in one step. R to the power of 10, so 5 to the power of 10, and multiply the angle by 10. Well, chuck it in the calculator and we're done. That was very easy. The new concept that we're going to be covering today is about finding complex roots. Here, when we are looking at these, what we want to do is we want to take a complex number by some fractional power. Let's first have a look at this equation so we can kind of slowly guide our way into this concept. Z to the power of 4 is 1. Well, what does that mean? Here are all the answers. 1 to the power of 4 is 1. Negative 1 to the power of 4 is 1. Also I and negative I to the power of 4 is 1. But how did I get to these solutions? Let's have a look. The position of, so the opposite of power of 4. Well, that would mean the fourth root, right? Why can't we just take the fourth root? Let's try it. Have a look. We have z to the power of 4. We take the fourth root, so we take the fourth root on the other side. But the fourth root of 1, well, that's just 1. Negative 1. What about I and negative I? They didn't come up here. Should they? Let's have a look. In order for us to find roots of complex numbers, we actually need all the information that the complex number is giving us. The complex number here at the top, this is not everything we know. And remember, I promised you one concept where we're going to have to use the general argument instead of just the principal argument. Well, here it is. We need to use the general argument for our number. So our complex number z is then r cis theta plus 2n pi, where n is an integer. So here we're going to have theta, our principal angle, and we're adding 2 pi n amount of times. Now, let's have a look at how we can do this. If we have a step-by-step formula, this would be it. If you're ever asked to find the roots of complex numbers, you need to make sure you follow these 3 steps. The first step is write your complex number in polar form. You want to write z to some power is equal to r cis theta plus 2n pi. So polar form and general angle form. So this is the first step over here at the top. Once we have this, we can use the Moivre's theorem and apply the rule just like we did before, but like I said, this time we're going to have a fractional power. If we have z to the power of a, the opposite would be the 8th root, or putting the power to the power of 1 over a. So applying our theorem here will give us that r to the 1 over a cis, well, here we have 1 over a is our power, so we multiply it by our angle. Simplifying, we get this equation here. Now, once we have applied the theorem, we then need to substitute in values for our n. And that depends on what the value is for the power. Remember, if we have z to the power 4, we're expecting 4 roots. If we have z cubed, we expect 3 roots. Something with a squared, you know, as a parabola or a quadratic has 2 roots. So whatever the value is, that's how many solutions we expect. The one thing that you still need to remember is that we somehow need to start with 0, counting up until the number that we had minus 1. So in this case, it would have been a minus 1. It doesn't really matter if you start with 1 and go all the way till a, but then the last one is not going to have the principal argument. If you follow the structure from 0 all the way till the power minus 1, you're going to already have your answers in the principal argument. So that will help. So let's have a look here. I've chucked the rule up at the top, so if you need to, you can spy on there. Let's have a look at our first example. Z to the power 4 is 1, which we still haven't been able to solve. Let's apply the steps at the top and see if we get all of our answers. Step 1 says we need to write z to some power is equal to polar form with a general argument. So 1 is a real number. So remember, this is the special form. And at this point, I need you to have learned that a real number has angle 0 if it's positive, and plus or minus pi you can choose if it's negative. Also, the radius, the modulus, is the same as the real number itself because we don't need to do Pythagoras theorem on the horizontal and vertical axis. So, as long as you can write your 1 as 1 cis 0 plus 2 and pi, everything else will now fall into place quite easily. Our second step is applying the Moivre's theorem. So what does that mean? We have z to the power 4 here, so we need to apply everything to the power of 1 over 4. So the modulus is going to be 1 to the 1 over 4. And again, we are going to be, if you look at this part of the equation at the top, we're going to be dividing by 4. Awesome. So putting all the equation parts together, substituting in our values, and simplifying a little bit, we can get these. Now, remember we have a power of 4, so we expect our 4 solutions. Let's see what happens if we substitute the values in. Again, we start with 0 and we count all the way till 3 because that's one value less than the power of 4. Let's substitute in and let's do it in one go because you can check that you can substitute on your own. Pause the video if you have to. Putting our angles together in the calculator will help us here. And remember, 1 to any power is 1, so that's why I didn't have the power here. So we're going to get 1 cis 0, 1 cis pi over 2, 1 cis pi, and 1 cis 3 pi over 2. Well, how do we get these values from this again? Well, remember, what does cis mean? Cis means we have cosine times the modulus plus I sine times the modulus is our real and imaginary parts. However, you should recognize these angles because I gave them to you as special angles. And if you've forgotten, make sure you go back to your notes or back to the video so you can learn these for good, so you don't struggle in the exam. If we have the angle 0, that's a real number that's positive. Having an angle pi or negative pi is a real number that's negative. Pi over 2 is your I, and negative pi over 2 or 3 pi over 2 is your negative I. Now, in some situations, you would be required here to write this as your principal argument. And remember, I usually consider the principal argument from negative pi to pi. This is clearly not from negative pi to pi. You would have to subtract 2 pi here to get negative pi over 2. However, I'm going to leave it as this because the marking schedule for these exams usually allow you to write these in this form. And if you find the final answer, it doesn't actually matter if you do cosine of 3 pi over 2 or cosine of negative pi over 2. Remember, the answer is going to be the same in rectangular form. Now, there's just one remark that I wanted to make. A lot of people will be easily remembering that you have to go from 0 all the way till 4, or well, 3 in this case, 1 less than the power. You could also start with 0, then do 1, negative 1, 2, negative 2, 3, negative 3, and so on for the values that you're substituting in for n. This will ensure that your principal value, your principal argument, is in the form of minus pi to pi. So whichever way you want to do, it's up to you. If you want to make sure that you are getting it in the right form, use the alternating whole numbers. Okay, here's an example of a question that you might get in an exam. Z to the power 4 plus 81k to the 8 is equal to 0. Well, what's the first step? Remember, we need to write z to the power 4 is equal to a number, but we want it in polar form, and we want this in general argument form. So first of all, if I move this over, I'm going to get negative 81k to the 8. Well, let's inspect this. What kind of number is this? Well, we see k to the power of 8. Anything with an even power is going to be an even number. Sorry, my bad. Everything with a power of an even power, we're going to get a number that is positive. That's what I meant to say. The other one is probably still true. I'll have to check that one. Write it in the comments if you think any number to the power of 8 is going to be an even number. Okay, so now remember that we wanted to write this in polar form. So here we're going to have to check. K to the power of 8 is always positive. Multiplying by negative 81 is always going to be a negative number. And k here is real, so we're going to just have a negative real number. So where are we? We're actually on the real axis, so our modulus is just the positive version of what we have before. For the angle, well, we have a negative real number, so the angle is going to be pi. And here again is our explanation for this step. So the argument here, the principal argument is pi. But what we need is we need to write this with the general argument. So we're going to get 81 k to the 8 says pi plus 2n pi, where n is an integer. This is our first step, writing it in the form, polar form with a general argument. The next step is we need to apply de Moivre's theorem. Here we have to the power of 4, so the opposite is to the power of a quarter. So let's apply this rule. The modulus is going to have a power of 1/4, but in the inside, in the argument, we multiply by that power. Remember, that was de Moivre's theorem. Well, here we can simplify a little bit. 81 to the power of 1 over 4, just chuck that in the calculator, it's going to be 3. K to the power of 8 to the power of 1/4. What do we do if we have a power to another power? We multiply the powers. 8 times 1/4 is going to be 2. So we have 3 times k squared. Now we look at the angle. Well, here we can just put the 4 at the bottom, expand the top if we have to, and just make it a little bit easier. Then we get to this expression at the top. Remember, now we need to substitute in our values n from 0 till 3. These are the steps that I've taken here. And all I've done now is I have used the argument and I've substituted in 0, 1, 2, 3 and put this in the calculator, and I've written my final answer. This will give you full marks. But remember, if you want this in the principal argument from negative pi to pi, you should use z0, z1, z minus 1, and then z2. Awesome. How do we solve polynomials with complex roots? So what we did before is we had an expression for a complex number and we wanted to take the root of a complex number. Now we're going to be solving a polynomial that might have complex roots. Let's have a look at this one here. We have x squared plus x plus 1 is 0. And we solved this one, or a very similar one before, and we used the quadratic formula. We're going to actually do the same here, but I would like to make a note that you can just use the calculator here or the quadratics formula and get the answer, even with complex numbers. However, if you're not sure on how to put your calculator in complex mode, make sure that you check out the video that I've left in the course, where you can find the link below to the full course. Make sure you check out the complex number calculator videos. Here I've chucked it in. We get these two as our answers. Now, there's something here that we can notice. Complex roots for any kind of polynomial always come in pairs. If you have one complex root, you have another one. And it's the same one, well, almost, it's the complex conjugate. So, if you have any root in your polynomial that is complex, then you immediately know a second root, which is the conjugate of this. So, here now we have a power of 3. We have a cubic. Now, a cubic, we're going to expect 3 roots. Now, if they're all real, then there's no problem. But if one of them is complex, we know that there's a second one that needs to be complex, leaving us with 1. This one has to be a real root. It can't be complex as well, because then we would have a fourth option, its conjugate. So if we look at the options here, we have -1i and -i, and these are your real root and your conjugates. Make sure that you know that a cubic has 3 roots where 1 must be real. It could be all 3 real, but it can only be 2 conjugates making 2 roots and 1 other being real. Awesome. That leaves us to almost the end of this topic. We're going to be talking about the locus in our next video, so make sure that you check out the link below with our structured course, all of the courses, videos together in one place, and you can log in, save your progress, come back later, and we have extra practice examples. We have flashcards for all the rules, so you remember those for your exams and you're always prepared. So make sure you check out the link below and log in to watch your videos there. I'll see you in the next one.